Take a look at the gold ring on your finger, or the platinum necklace you're wearing. They are shimmering, silent, and elegant. But there is a truth few realize for that jewelry to exist. The universe had to endure one of its most violent tragedies. Our sun, as grand and scorching as it may be, is actually too weak to create gold. The most precious things on Earth weren't born within the glow of living stars. They are the ashes of dead ones. Today, we travel back 130 million light years to witness a death dance between the two densest objects in the cosmos. To understand why every gram of gold you hold is, in fact, a miracle forged from violence and darkness. To understand where gold comes from, you first have to understand something about how the universe builds things. Because it turns out the universe is not a single factory. It is a collection of very different factories, each one operating under completely different conditions, each one producing a completely different set of products. And the rules about which factory makes which element are surprisingly strict. The universe has been running these factories for 13.8 billion years, and the output of each one is written into the composition of every rock, every ocean, every living cell on this planet. The lightest elements, hydrogen and helium, came first. They were assembled in the first few minutes after the Big Bang, when the universe was still a dense, blindingly hot plasma, and the physics was simple enough that protons and neutrons could fuse together almost spontaneously. That process lasted roughly 17 minutes. 17 minutes, a time span shorter than most commutes. And in those 17 minutes, the universe produced the raw material for every star that would ever exist. After that window closed, the universe cooled too fast for fusion to continue, and the first chapter of element building closed with it. Everything from hydrogen to helium, about 92% of all the atoms in the observable universe, was locked in during those 17 minutes. The remaining 8%, every other element on the periodic table, had to wait for something more dramatic. Then came the stars. Stars are fusion reactors that run on gravity. A star begins its life as a cloud of mostly hydrogen gas. And when that cloud grows dense enough, gravity compresses the center until the temperature reaches about 10 million degrees, the threshold at which hydrogen nuclei begin fusing into helium. That fusion releases energy, which pushes outward against gravity, and the star finds a kind of equilibrium, inward pull, balanced against outward push, sometimes for billions of years. The sun has been burning in this equilibrium for 4.6 billion years, and has roughly 5 billion more to go. When the hydrogen runs out, the star compresses further, the temperature rises higher, and helium begins fusing into carbon. Carbon fuses into oxygen, oxygen into neon, neon into silicon, silicon into sulfur, each stage requiring a higher temperature than the last, each stage happening faster than the one before it. A star might spend 10 billion years burning hydrogen and only a few thousand years burning silicon. The entire later history of a massive star after hydrogen is a series of progressively more desperate attempts to hold off gravitational collapse, each fuel lasting a shorter time than the last, like a fire burning through progressively less efficient fuel as it runs out of wood. At the end of that chain sits iron, and iron is where the story changes. Iron is, in a very specific sense, the most stable nucleus in existence. Fusing elements lighter than iron releases energy. That is what makes stars shine. What makes hydrogen bombs detonate? What keeps the universe warm? But fusing iron consumes energy rather than releasing it, because the iron nucleus is already at the lowest possible energy state for a nucleus of its size. and pushing it toward a heavier configuration requires an energy input that no star can sustain. A star that has built up an iron core has, in effect, run out of road. The fusion stops, the outward pressure disappears, and gravity, which has been held at bay for millions or billions of years, wins instantly, collapsing the core in less than a second. Not gradually, not in stages. The core goes from the size of the Earth to the size of a city in under a second, and the infall velocity approaches a quarter of the speed of light. It is the fastest structural collapse of any large object in the known universe. That is what a supernova is. The outer layers of the star, falling inward at a quarter of the speed of light, rebound off the suddenly rigid core and explode outward with enough force to briefly outshine the entire galaxy. In that explosion, the temperatures and pressures are high enough to fuse some heavier elements: copper, zinc, a handful of others, and scatter them across light years of space. A supernova visible from Earth can outshine every other star in the night sky combined, and the shockwave it sends through the interstellar medium can trigger the formation of new stars and planetary systems across a volume of space measured in light years. Supernovae are, by any ordinary measure, among the most spectacular and energetic events in the universe, and they cannot make gold, the elements heavier than iron that we consider precious, the ones rare enough to use as currency, dense enough to shield nuclear reactors, useful enough to wire every electronic device ever made. Those require a process so extreme that even a supernova cannot produce them in meaningful quantities. The temperatures in a supernova are high enough, but the neutron density is too low, and the time scale of the explosion is too short for the relevant nuclear reactions to run to completion. Supernovae scatter what they have quickly and move on. The heavier elements require something more sustained, more neutron-rich, more violent in a concentrated and specific way. For most of the 20th century, astrophysicists knew that these elements had to exist somewhere in the universe. The periodic table was complete. The atoms were real. The measurements were certain. But the mechanism that created them remained genuinely unknown. The process they were looking for was called rapid neutron capture, or the R process. And the theory was solid if you could expose atomic nuclei to an overwhelming flood of free neutrons, fast enough that the nuclei absorbed neutron after neutron before they had time to decay. You could build elements far heavier than iron in a matter of seconds. The math worked. The physics worked. The only problem was finding a place in the universe where conditions like that actually existed, where the neutron density was high enough, the temperature was in the right range, and the timescale was fast enough to produce the R process before the environment dispersed. A supernova was a candidate for decades. The temperatures are right. The neutron density is high in some regions. The timescales are fast, but the numbers never quite added up. Supernovae alone could account for some of the heavy elements, but the quantities were consistently too low. The distribution across the galaxy too uneven. The chemical fingerprint slightly wrong in ways that kept showing up in observations of old stars. Something else had to be contributing. Something producing heavy elements in enormous quantities, but happening very rarely. Rare enough to explain why gold is scarce. Violent enough to explain why the quantities, when produced, are staggering. The answer was sitting in a corner of astrophysics that most people had never heard of. And to understand it, you first need to understand the thing that does the colliding. The object at the center of this story, the densest thing in the universe that is still, technically, a thing. Before getting to the collision, it is worth spending a moment with what a neutron star actually is. Because neutron stars are genuinely one of the strangest objects in the known universe. And understanding their strangeness is what makes the collision so extraordinary. Most objects in the universe are extreme in one direction or another. Black holes are incomprehensibly massive. White dwarfs are extraordinarily hot. Magnetars have field strengths that would strip electrons from atoms at a distance. But neutron stars occupy a unique position in the landscape of cosmic extremity because they are extreme in almost every measurable way simultaneously, while still being objects with surfaces and structures that can, in principle, to be described. When a massive star, something between 8 and 20 times the mass of the Sun, reaches the end of its life and its core collapses. The result depends on exactly how massive that core is. If it is too massive, it collapses all the way through and becomes a black hole, a point of infinite density from which nothing escapes. But if the core falls within a certain mass range, roughly between 1 and 3 solar masses, something different happens. The collapse is halted by a quantum mechanical effect called neutron degeneracy pressure, which is essentially the universe's refusal to allow two neutrons to occupy exactly the same quantum state at the same location. As the neutrons are compressed together, they resist further compression with a force that grows sharply as the density increases. And at a certain density, that resistance is strong enough to halt the collapse entirely. The collapse stops, the core bounces, and what remains is a neutron star. A neutron star is approximately 16 kilometers across. That is roughly the distance from one end of a city to the other. The kind of distance a fast runner covers in about an hour. Inside that sphere, compressed to the density of an atomic nucleus, sits a mass between 1 and 2 times the mass of the Sun. A star that once stretched across hundreds of millions of kilometers, across a volume larger than the distance from Earth to the Sun, now packed into something you could drive across in 20 minutes on a highway. The compression ratio involved in creating a neutron star from a stellar core is comparable to compressing the entire population of Earth into a space the size of a sugar cube. The numbers describing a neutron star's density are so extreme that ordinary units stop being useful. The density at the center of a neutron star, approximately 3 times 10 to the power of 15 grams per cubic centimeter, means that a single teaspoon of neutron star material transported to Earth would weigh roughly as much as 7 million elephants. Another way to hold that number: all the water in all the Earth's oceans, compressed to neutron star density, would fit inside a space roughly the size of a sports stadium. The surface gravity is 100 billion times stronger than Earth's gravity, which means the escape velocity from the surface exceeds half the speed of light. A mountain on a neutron star can be at most a few centimeters tall before the gravity crushes it flat. The most rugged terrain on a neutron star is smoother, relative to the star's size, than a billiard ball. The structure inside a neutron star descends through layers of increasing strangeness as you move from the surface to the center. The outer crust is a crystalline lattice of ionized atomic nuclei and electrons. A solid, in a sense, though nothing like any solid found on Earth, because the pressures involved would vaporize any earthly material instantaneously. Deeper down, the nuclei begin to dissolve as the density climbs, and the material transitions into a fluid of almost pure neutrons. A superfluid, in fact, that flows without viscosity through the interior in ways that produce observable effects in the star's rotation. At the very center of the most massive neutron stars, the density may be high enough for an even more exotic phase transition. The neutrons themselves may dissolve into their constituent quarks, creating a state of matter called quark matter that has never been observed in any laboratory and may exist nowhere else in the current universe. Some models even predict more exotic states: color superconductivity, strange quark matter, hyperons, each representing a form of nuclear matter that sits beyond the reach of any experiment currently conceivable on Earth. All of this sits inside a sphere the size of a city. Spinning, newly formed neutron stars rotate up to 700 times per second, faster than a kitchen blender on maximum speed, faster than the fastest electric motor ever built, and slow down gradually over millions of years as they radiate energy. They have magnetic fields 1,000,000,000,000 times stronger than Earth's, strong enough that the magnetic force at the surface would be lethal from a distance of 1,000 kilometers, strong enough to distort the shapes of the electron orbitals in atoms. The radiation they emit, channeled by those magnetic fields into narrow beams that sweep across the sky like cosmic lighthouses, produces the pulsar signal. A radio pulse so regular that when it was first detected in 1967, astronomers briefly and seriously considered the possibility that it was produced by an intelligent civilization. They are, in every measurable way, the most extreme objects in the universe that are still technically objects, things with surfaces and structures and interiors, rather than the pure gravitational singularity of a black hole. And the fact that they exist at all, that the quantum mechanical rules of the universe happen to produce a stable configuration of matter at this extraordinary density, is itself one of the more remarkable coincidences in the physics of our universe. And sometimes, two of them find each other, and what follows makes everything described here look like a gentle preamble. When a massive star system contains two stars, a binary system, which describes roughly half of all star systems in the Milky Way, and both stars are massive enough to end their lives as neutron stars. The result is a neutron star binary, two of the densest, most extreme objects in the universe, locked in orbit around each other, separated by distances that shrink over astronomical timescales through one of the most elegant mechanisms in all of physics. The mechanism is gravitational waves, general relativity. Einstein's description of gravity, published in 1915 and confirmed repeatedly in the century since, treats gravity as a curvature in the fabric of space-time rather than a force transmitted between objects. Massive objects curve space-time around them, and other objects move along those curves. When two massive objects orbit each other, the accelerating masses continuously disturb the space-time around them, producing ripples in that fabric, gravitational waves, that propagate outward at the speed of light, carrying energy away from the system in the same way that an accelerating electric charge radiates electromagnetic energy. The critical consequence is this: as the system loses energy to gravitational wave emission, the orbit shrinks. As the orbit shrinks, the objects move faster. As they move faster, the gravitational wave emission intensifies, carrying away more energy, shrinking the orbit further still. The process is self-reinforcing and, once begun, completely irreversible. A slow-motion death spiral encoded in the geometry of space-time itself, running from the moment the binary forms to the moment it merges, with nothing that can interrupt it. For two neutron stars, this process unfolds over timescales that dwarf human comprehension. A newly formed neutron star binary might begin with an orbital separation of hundreds of thousands of kilometers, completing one orbit every few hours. At that separation, the gravitational wave emission is so weak that it would take hundreds of millions of years, sometimes billions, for the orbit to shrink to the point of collision. The spiral is happening constantly, continuously, at every moment, but at a pace so slow that across the entire span of human civilization, from the first cities in Mesopotamia to the present day, the orbital separation would decrease by less than the width of a human hair. Every orbit, the two stars come back together slightly closer than before, by an amount so small it cannot be directly measured, but real nonetheless, accumulating over geological timescales into a separation change of kilometers, then thousands of kilometers, then the final approach, The first observational confirmation that this process was real came in 1974, when Russell Hulse and Joseph Taylor discovered a binary pulsar, a neutron star in orbit around another neutron star, and measured, over the following years, that the orbital period was decreasing at exactly the rate predicted by general relativity for gravitational wave emission. The measurement matched Einstein's equations to within a fraction of a percent. It was the first indirect evidence that gravitational waves existed, and it won the Nobel Prize in Physics in 1993. Then, in the final stages, everything accelerates. As the two stars close to within a few hundred kilometers of each other, the orbit begins shrinking measurably on human timescales. Years, then months, then days, then hours, at a separation of around 20 kilometers. The orbital frequency has climbed from once every few hours to nearly 1,000 revolutions per second. The gravitational wave signal, which started at frequencies far too low for any detector on Earth to register, has swept upward through the frequency range of human hearing. And if you converted it to audio, it would sound like a rising tone, a chirp climbing in pitch over the course of the final 100 seconds, louder and faster and higher until the moment of merger. Not the chirp of a bird, more like the tone of a musical instrument being played at rapidly increasing tempo, the notes blurring together in the final seconds into something continuous and urgent. In those final 100 seconds, the two stars complete roughly 3,000 orbits. Each orbit is tighter than the last, each revolution faster, each pass closer. The tidal forces between them begin distorting their shapes, stretching them from spheres into elongated blobs, raising kilometer-high tides on their surfaces as each star's gravity reaches across the narrowing gap to deform the other. The magnetic fields, already trillions of times stronger than Earth's, begin interacting across the closing distance, generating electric currents and fields of extraordinary strength that heat the surrounding space. Charged particles are accelerated to near light speeds along the tangled field lines. The space between the two stars becomes a violent electromagnetic storm even before the surfaces touch. And then, at the point where the two surfaces finally touch, where 16 kilometers of compressed nuclear matter meets 16 more kilometers of compressed nuclear matter at a closing velocity of tens of thousands of kilometers per second, the collision begins. What happens next takes less than a second, produces more gold than the Earth contains by a factor of several thousand, and releases more energy than the Sun will emit across its entire 10 billion year lifetime. The word kilonova was coined by astrophysicists to describe something that is, in a specific sense, a failure of language, a phenomenon so unlike existing categories that the available vocabulary simply did not fit. It is not a nova, the relatively modest thermonuclear explosion that happens on the surface of a white dwarf star when it accumulates too much hydrogen from a companion. It is not a supernova, the catastrophic death of a massive star, the event that briefly outshines a galaxy and scatters half a solar mass of material across light years. It is something in between those scales, but fundamentally different from both. And the kilo prefix, 1,000 times, is meant to convey that it is roughly 1,000 times brighter than a classical nova. That framing is accurate but slightly misleading, because it implies the event is merely a brighter version of something familiar, when in reality the mechanism is entirely distinct. In reality, a kilonova at peak brightness outshines the Sun by approximately 200 million times, a number so large that it requires a moment to sit with 200 million suns, all blazing from a single point in the sky. And yet a supernova outshines the Sun by 10 billion times, 50 times brighter than a kilonova, which means that kilonovae for most of the history of observational astronomy, were too faint to reliably detect at the distances where they occurred, routinely outcompeted in brightness by the dying stars nearby. The kilonova's significance lies not in its brightness but in what it produces, and in the specific combination of conditions that make that production possible. When two neutron stars merge, the collision does several things simultaneously in the first fractions of a second. The combined mass, now exceeding the mass of two suns compressed into a space smaller than a city, either collapses directly into a black hole or briefly forms a hypermassive neutron star, an object even more extreme than either of its parents, spinning at extraordinary speed and supported against collapse by centrifugal force and thermal pressure, before collapsing a few milliseconds later as it radiates away the energy that was holding it up. Which outcome occurs depends on the combined mass and on the poorly understood equation of state of nuclear matter for mergers near the threshold. The hypermassive neutron star may survive for up to a second before collapsing, and in that second, it radiates gravitational waves at frequencies that carry direct information about the internal structure of nuclear matter. The collision launches jets of material moving at close to the speed of light along the rotational axis. Relativistic jets punching through the surrounding material and producing a burst of gamma-ray radiation. A short gamma-ray burst that can be detected across billions of light-years. These gamma-ray bursts, which had been observed since the 1960s and remained mysterious for decades, are now understood to be the observational signature of neutron star mergers seen from a particular viewing angle, the end-on view, looking straight down the barrel of the jet, and the violent distortion of the newly merged object flings material outward in all directions, a wind of hot, neutron-rich matter expanding at up to a third of the speed of light, carrying with it the raw ingredients and the conditions necessary for the most productive nuclear forge in the universe. That wind, the kilonova ejecta, contains roughly 1 to 10% of the sun's mass. Launched at velocities that would carry it from the Earth to the Moon in under 2 seconds. Dense with free neutrons at concentrations that exist nowhere else in the accessible universe. In that ejected material, in the first second after the collision, as the wind expands outward and the temperature drops from billions of degrees to hundreds of millions, the R process runs, and in running, constructs the lower half of the periodic table from scratch. The signature of this process is visible in the light the kilonova emits, and it is unlike anything else in astronomy's catalogue. In the first hours, the kilonova glows blue, the color of light from hot plasma, the same kind of glow you see in very hot stars. But over the following days, as the ejecta expands and cools, and the heavy elements freshly synthesized in the R process begin to dominate the opacity of the material, the color shifts from blue to a deep, sustained red, a ruby glow that persists for days and is the visual signature of lanthanides and actinides freshly assembled from neutron capture. These elements, with their extraordinarily complex electron structures, absorb and re-emit light at longer wavelengths so efficiently that they push all the radiation toward the red end of the spectrum, turning the kilonova the color of a garnet or a dark ruby. And that color, to any astronomer who knows what they are looking at, is the color of gold being made. A kilonova is, in the most literal sense, a self-illuminating forge, an explosion that lights itself with the radioactive decay of the very elements it is creating. On August 17th, 2017, at 12 minutes past 12 in the afternoon Universal Time, 2 detector facilities in the United States, one in Hanford, Washington, and one in Livingston, Louisiana, separated by 3,000 kilometers, simultaneously registered a distortion in space-time so small it would be described as a fraction of the width of a proton stretched across a distance of 4 light-years. The signal lasted 100 seconds and swept upward in frequency from 24 Hz to several hundred Hz before going silent. The LIGO detectors, the Laser Interferometer Gravitational Wave Observatory, a pair of instruments that use laser light to measure the distance between mirrors suspended in near-perfect vacuum across 4-kilometer baselines, had just recorded the gravitational wave signal from two neutron stars 130 million light-years away, completing their final 3,000 orbits before merging. To appreciate what this detection represents physically, consider what it was measuring. The gravitational waves from GW 170817 stretched and compressed the 4-kilometer arm of the LIGO detector by approximately 1,000th the diameter of a proton. A proton is roughly 1 femtometer across, 1/1,000,000th of a billionth of a meter. LIGO detected a displacement 1,000 times smaller than that. Across a 4-kilometer baseline, it is, by some measures, the most precise length measurement ever made by any instrument in human history, and it was measuring a ripple in the geometry of space produced by two objects, the size of cities, colliding 130 million light-years away. 1.7 seconds after the gravitational wave signal ended, the Fermi Space Telescope, orbiting Earth, scanning the sky for gamma rays, detected a short burst of gamma radiation from the same direction. The delay of 1.7 seconds between the gravitational wave arrival and the gamma ray arrival, across 130 million light-years of travel, confirmed that gravitational waves travel at the speed of light to within 1 part in 10 to the 15th. Einstein's general relativity had predicted this in 1915. The measurement confirmed it to a precision that exceeded all previous tests combined, delivered incidentally alongside an entirely different first-in-history observation. 11 hours after the merger, the first optical light appeared, a bright blue point source in the outskirts of a galaxy called NGC 4993, a galaxy catalogued in the 1980s and sitting unremarkably in the southern constellation Hydra, roughly 130 million light-years distant. The light was blue, the initial hot emission from freshly ejected plasma. Within hours, 70 observatories around the world had turned to look, spanning every wavelength from radio to gamma ray, from facilities on every continent and in orbit above the atmosphere. It was the most intensely observed astronomical event in history, studied simultaneously by more instruments than any previous cosmic event. Over the following days, as the kilonova expanded and cooled, the color shifted from blue to red, the exact signature predicted for heavy element formation. The ruby glow of lanthanides and actinides, freshly synthesized in the neutron wind. Spectroscopic analysis confirmed what theorists had predicted: strontium, a heavy element that sits well above iron on the periodic table, was present in the ejecta. Subsequent analysis found signatures consistent with gold and platinum. The quantities were extraordinary. The kilonova produced an estimated 16,000 times the mass of the Earth in heavy elements, of which dozens of Earth masses consisted of gold and platinum alone. In 1 second, in one event, the universe had manufactured more gold than has ever existed in the entire history of human civilization, and scattered it across a volume of space larger than the distance light travels in a year. This event, designated GW 170817, was the first time in history that a single astronomical event had been observed simultaneously through gravitational waves and through light. It marked the birth of what scientists now call multi-messenger astronomy, the ability to study the universe through multiple fundamentally different information carriers simultaneously, the way a person uses multiple senses to understand a single event. Before GW 170817, astronomy was a discipline that worked almost entirely through electromagnetic radiation, light in its various wavelengths, supplemented by the occasional cosmic ray or neutrino. After GW 170817, the field had a new channel, carrying information that electromagnetic radiation cannot carry, about phenomena that electromagnetic radiation cannot directly observe. It was as if humanity, which had spent all of its history experiencing the universe through a single sense, had suddenly and irrevocably developed a second one. And the first thing that second sense showed us, with perfect clarity, was exactly where gold comes from. The universe had been making gold this way for billions of years. The only thing that changed on August 17th, 2017, was that we were finally there to watch the R process. Rapid neutron capture is one of those mechanisms in physics where the description sounds almost too simple for the results it produces, which is part of what makes it so elegant and so strange. The basic operation can be stated in a sentence: expose atomic nuclei to an overwhelming flood of free neutrons, fast enough that they absorb neutron after neutron before having time to decay, and the nuclei grow heavier and heavier until the neutron supply runs out, at which point they decay down through a cascade of radioactive transformations into stable heavy elements. The sentence is accurate. The reality it describes is the most productive elemental synthesis process in the universe. The conditions required are specific in a way that explains why the R process happens so rarely. The free neutron density needs to be extremely high, around 10 to the power of 20 neutrons per cubic centimeter, which is billions of billions of billions of neutrons packed into a space the size of a marble. The temperature needs to be in the range of 1 billion to 10 billion degrees Kelvin, hot enough that the physics of nuclear reactions runs at full speed, but cool enough that the nuclei being assembled are not immediately destroyed by the energetic photons surrounding them. And the event has to happen fast. The entire R process runs and produces its full inventory of heavy elements in the first few seconds after the collision, before the ejector has expanded to the size of a small planet, and the density has dropped too far for the reactions to continue. At those temperatures and densities, the R process runs at a pace that seems almost incomprehensible. From a laboratory perspective, a nucleus can go from iron to gold, absorbing more than 160 neutrons and undergoing dozens of radioactive decays in less than a second. Consider what that means in terms of nuclear chemistry. In a particle accelerator, producing a single exotic neutron-rich nucleus takes days of beam time and produces results measured in individual atoms. In a kilonova, the entire lower half of the periodic table is assembled from pre-existing lighter nuclei in a volume of space comparable to a small city, in a time comparable to the interval between heartbeats. What happens physically, step by step, is this: the neutron-rich material ejected from the merger site expands rapidly outward, and as it expands, it cools. In the first milliseconds, the temperature is still above a few billion degrees, hot enough that even photons have enough energy to break apart complex nuclei as fast as they form. The R process cannot begin yet. Any heavy nucleus assembled in that environment is immediately photodisintegrated back into lighter components. Then, as the temperature drops below roughly 3 billion degrees, the photodisintegration rate falls below the neutron capture rate, and nuclei begin to accumulate neutrons faster than they are destroyed. Each nucleus immediately begins absorbing the surrounding free neutrons, building upward through the chart of nuclides, the map of all known and theoretical atomic nuclei, along a path far from the stable isotopes familiar from chemistry textbooks. The nuclei being assembled here are neutron-rich in the extreme isotopes so far from stability that they have never been produced in any laboratory on Earth in meaningful quantities, each one existing for a fraction of a second before the next neutron arrives, sitting on the edge of falling apart but stabilized momentarily by the extraordinary neutron flux surrounding them. The path of the Ra process through the chart of nuclides runs along the neutron drip line, the boundary beyond which adding another neutron causes immediate neutron emission, zigzagging between stability and instability at extraordinary speed. Then the cascade begins, as the ejector expands and the free neutron supply runs out. These exotic neutron-rich nuclei are left stranded far from stability on the chart of nuclides, and they begin the long journey back, through a series of beta decays, in which a neutron converts into a proton while emitting an electron and an antineutrino, shifting the nucleus one step towards stability. Each beta decay changes the element. Adding a proton changes the atomic number, transforming one element into the next, and the cascade of beta decays threads its way through dozens of intermediate elements before arriving at a stable configuration. Gold, with 79 protons, is assembled through this cascade from nuclei that started with far fewer protons and far more neutrons, transformed step by step through the beta decay chain over timescales that range from milliseconds to hours. Uranium, with 92 protons, emerges from the same process but through a longer and more complex decay chain, one that produces several intermediate elements: radium, radon, polonium, bismuth, before arriving at the stable lead isotopes that are uranium's ultimate decay products. The 2023 kilonova associated with gamma-ray burst, GRB 230307A, provided direct spectroscopic evidence for tellurium, one of the rarest elements on Earth, sitting at atomic number 52 in the kilonova ejecta, observed through the James Webb Space Telescope at infrared wavelengths that are invisible from the ground. Tellurium sits precisely at a position on the chart of nuclides, where our process models predict a concentration of heavy elements, at a so-called magic number of neutrons, where nuclear structure makes the nuclei particularly stable and causes the R process path to linger momentarily. Its detection confirmed not just that the R process was running, but that it was running in the specific quantitative way theorists had calculated decades earlier. The Webb telescope, designed to study the earliest galaxies in the universe, had been pointed at a kilonova and returned data confirming nuclear physics predictions made in the 1950s. The numbers produced in a single kilonova are staggering in a way that becomes easier to feel through comparison. All of the gold ever mined in human history, every coin struck by every civilization, every gold bar in every central bank, every wedding ring, every trophy, every crown, amounts to approximately 200,000 metric tons. A single kilonova produces, conservatively, several tens of Earth masses of gold, and one Earth mass is 6, followed by 21 zeros metric tons. A single kilonova produces, in less than a second, roughly 1 billion times more gold than all of human history has extracted from the Earth's crust. And it scatters that gold across a volume of space so vast that the fraction of it which eventually falls into any single planetary system is utterly negligible. And yet that negligible fraction is still more than enough to fill the Earth's oceans several times over, if it were concentrated rather than diluted. That is the forge. That is how it works. And the products of that forge are sitting in drawers and bank vaults and geological formations and human bodies all across this planet, waiting for someone to trace their ancestry back to the moment of their creation. The gold on Earth has a specific and somewhat surprising history that connects directly to the kilonova origin story. A history that involves 2 separate violent episodes, separated by roughly 600 million years, and a planetary process called the Iron Catastrophe that is one of the most underappreciated events in Earth's geological past. When the solar system was forming, roughly 4.6 billion years ago, the cloud of gas and dust that would become the sun and planets contained a mixture of elements inherited from billions of years of stellar evolution. The cumulative output of generations of stars, including heavy elements produced in kilonova events that had occurred long before the Sun was born. The presolar cloud that collapsed to form the solar system carried the chemical fingerprints of every astrophysical process that had operated in our region of the Milky Way across billions of years: carbon and oxygen from stellar winds, calcium and silicon from supernovae, gold and platinum and uranium from kilonova mergers that had scattered their debris across the galaxy long before any planet existed. As the Earth accreted from planetesimals, the rocky bodies that formed in the inner solar system from the solid fraction of that presolar cloud, it was initially a relatively homogeneous mixture of all these elements, distributed through the growing planet in roughly the proportions they appeared in the presolar cloud. But as the planet grew, the energy of accretion, the kinetic energy of billions of asteroid scale and larger impacts, converted to heat upon collision, began to melt the interior. A fully molten planet behaves like a liquid in a gravitational field. Heavy things sink, light things rise. In the case of the early Earth, iron, dense, abundant, and with a specific affinity for certain other metals, began sinking toward the center, dragging with it the elements that preferentially dissolve in molten iron rather than in silicate rock. This group of elements, called siderophiles, iron-loving elements by geochemists, includes prominently gold, platinum, iridium, osmium, ruthenium, rhodium, and palladium, essentially the entire suite of precious metals that a kilonova produces in abundance were siderophilic enough to follow the iron downward. This process, the iron catastrophe, happened roughly 30 to 50 million years after the Earth formed, a geological eye blink, and it was thorough. When it was complete, virtually all of the original gold in the proto-Earth had sunk to the core, a region roughly the size of Mars, sitting at the center of the planet at temperatures above 5,000 degrees and pressures several million times atmospheric. The iron core of the Earth, occupying roughly 16% of the planet's volume, contains enough gold to coat the entire surface of the Earth to a depth of roughly half a meter. Gold that is completely and permanently inaccessible to any human technology. Sitting under nearly 3,000 kilometers of rock and iron, at conditions that would instantly vaporize any material we could send there. The gold that exists in the crust, the gold that has been mined, traded, worn, fought over, and used as currency throughout all of human history, is almost entirely the product of a different event, the late Veneer, in the period roughly 4 to 4.1 billion years ago, after the iron catastrophe had already concentrated gold into the core. The inner solar system was struck by a sustained barrage of asteroid and comet-sized impactors, material left over from the formation of the outer solar system, perturbed inward by the gravitational influence of Jupiter. This bombardment delivered a fresh supply of gold-rich material to the Earth's surface, after the differentiation that would have sequestered it was already complete, leaving the gold distributed through the mantle and crust in the concentrations we observe today. Even after the late Veneer, the gold in the crust is cosmically scarce. The average concentration of gold in the Earth's crust is 4 parts per billion by mass, meaning that for every billion grams of crustal rock, you find approximately 4 grams of gold. The gold deposits that miners exploit are enriched concentrations, places where geological processes, hydrothermal fluids circulating through cracks in cooling rock, volcanic activity, the slow grinding of tectonic plates, have concentrated gold by factors of hundreds to thousands above the crustal average, to levels where extraction becomes economically feasible. Gold veins form when hot water carrying dissolved gold percolates through fractures in rock and precipitates the metal as the temperature drops. The gold rush rivers that carried placer gold were concentrating the products of millions of years of such geological enrichment into accessible deposits. Every gram of that gold traces its ancestry through a chain of geological processes back to an asteroid bombardment 4 billion years ago, and through that bombardment back to kilonova events that occurred before the sun existed. Uranium tells a slightly different part of the same story, and it connects the kilonova to the present-day functioning of the planet in ways that most people have never considered. Uranium-238. The most abundant isotope of uranium was synthesized in the same R process environments as gold, in kilonova events, and possibly in rare types of supernovae, and incorporated into the forming Earth during accretion. But, unlike gold, uranium was not efficiently sequestered into the iron core. It has a strong chemical affinity for silicate minerals rather than for iron, and so it remained distributed through the mantle and crust as the planet differentiated, present in concentrations of a few parts per million in the continental crust and lower concentrations in the oceanic crust and upper mantle. There, it decays. Uranium-238 has a half-life of 4.5 billion years, almost exactly the current age of the Earth, which means that roughly half of the uranium present when the Earth formed is still here, releasing energy at every step of its decay chain. Thorium-232, another R process product with a half-life of 14 billion years, longer than the current age of the universe, decays alongside it. Together with potassium-40, these radioactive elements generate roughly half of the Earth's internal heat budget, the other half being primordial heat left over from accretion and the iron catastrophe, which has been leaking out through the surface for 4.5 billion years. That internal heat is what drives plate tectonics, the convection currents in the mantle, which drag the tectonic plates around the surface at roughly the rate your fingernails grow, 2 to 3 centimeters per year, are powered by the temperature gradient between the hot interior and the cooler surface. A gradient maintained by ongoing radioactive decay. The continents drift because uranium is decaying in the mantle beneath them. The Himalayas exist because Indian-Australian plate material, buoyed by the heat of radioactive decay in the underlying mantle, has been moving northward for tens of millions of years and colliding with Eurasia. The volcanoes of the Pacific Ring of Fire are driven by subduction, the sinking of oceanic plates back into the mantle, which itself requires the mantle convection that radioactive heating maintains. Without that heat source, the mantle would have cooled and solidified billions of years ago. Plate tectonics would have stopped. The long-term carbon cycle, the process by which carbon dioxide is pulled from the atmosphere through chemical weathering of rocks, carried down subducting plates into the mantle, and returned to the atmosphere through volcanic outgassing over millions of years, would have ceased. Carbon dioxide levels in the atmosphere would have dropped to near zero. Plant photosynthesis would have halted. The greenhouse effect that keeps Earth warm enough to have liquid water would have disappeared, and the planet would have frozen. The conditions for complex life would never have existed. The radioactive heat that keeps the Earth geologically alive, the heat that moves continents, builds mountains, sustains the carbon cycle, and created the conditions in which life evolved, is kilonova debris, still releasing the energy that was locked into exotic nuclei during a fraction of a second of neutron-star collision. Billions of years ago, the Earth is powered, in a direct and ongoing physical sense, by the afterglow of a cosmic event it witnessed only as a contribution to the dust cloud from which it was assembled. The scarcity of gold is one of those facts that seems self-evident. Gold is valuable because it is rare. It is rare because it is hard to find. And it is hard to find because deposits are geologically uncommon. That explanation is accurate at the scale of a mining operation or a commodity market, but it entirely misses the deeper reason. The cosmic reason, the reason that sits one level of causality upstream from everything the mining industry has ever measured. The actual reason gold is rare is that the event which creates it is extraordinarily uncommon, and understanding the frequency of that event explains, with remarkable precision, why gold is exactly as rare as it is, and why it cannot ever be much more abundant than it currently is. Supernovae, the explosions of massive stars, happen in the Milky Way at a rate of roughly 1 or 2 per century. That sounds infrequent from a human perspective, but across the 300 million year span of Earth's history since complex life began, there have been millions of supernovae in our galaxy, each one enriching the interstellar medium with the products of stellar nucleosynthesis: carbon, oxygen, neon, silicon, sulfur, calcium, iron, and a modest scattering of elements heavier than iron produced in the explosion's brief neutron-rich environment. The elements that supernovae produce in large quantities are the elements that are cosmically abundant. Oxygen is the third most abundant element in the universe by mass. Carbon is the fourth, and both owe their abundance largely to the fact that billions of supernovae have been scattering them across the galaxy for most of cosmic history. Neutron star mergers are different by roughly 3 orders of magnitude in frequency. In a galaxy like the Milky Way, the estimated rate of neutron star binary mergers is somewhere between a few tens and a few hundreds per million years, meaning that in the same 300 million years that saw millions of supernovae, there were perhaps only a few thousand neutron star mergers in the entire galaxy. Each one produced spectacular quantities of heavy elements. But the galaxy is enormous, a disk 100,000 light-years across, containing hundreds of billions of stars. And the output of those few thousand kilonova events was diluted into a volume so vast that the galactic gold concentration has remained at trace levels throughout the history of the solar system. There is an additional layer of rarity that makes the gold story even more specific. The R process requires a neutron-rich environment that ejects material at velocities high enough to escape the gravitational field of the merger remnant. In some mergers, particularly those where the combined mass exceeds a critical threshold and collapses directly to a black hole before much material can be ejected, the bulk of the neutron-rich wind falls back into the newly formed black hole rather than escaping into space. The heavy elements are synthesized but not delivered. Only mergers where the ejection is efficient, where the dynamics of the collision launch enough material at high enough velocity before the black hole forms, contribute meaningfully to the galactic heavy element inventory. The already rare merger events are filtered further by this efficiency criterion, leaving an effective source rate for gold production that is genuinely among the lowest of any elemental synthesis process in the universe. There is something almost philosophical about this rarity. If you sit with it long enough, the universe does not make gold sparingly because it is stingy or because gold has some special protected status. The universe makes gold sparingly because the conditions required for its synthesis, the specific combination of extreme neutron density, extreme temperature, and extreme velocity that constitutes the kilonova ejecta, can only be achieved by colliding 2 objects that are themselves the product of a long chain of stellar evolution. A massive binary star system, both stars massive enough to produce neutron stars, surviving the 2 supernova explosions that create them, remaining bound to each other through those explosions, and then waiting for gravitational wave emission to bring them together over hundreds of millions of years. The entire chain of events required to produce a single atom of gold is longer and more specific than the chain required to produce any lighter element. This is why there is no economically viable way to manufacture gold artificially, and why there will never be one. Nuclear transmutation can convert one element into another, and gold has in fact been produced in particle accelerators through neutron bombardment of platinum, a demonstration of the R process in miniature, but the quantities are subatomic. Producing a single gram of gold through artificial transmutation requires an energy input that exceeds the market value of that gram by a factor of millions. The universe makes gold in the only way gold can be made in meaningful quantities, by colliding two neutron stars under conditions that exist nowhere in the accessible universe except at the merger point itself. Conditions that require billions of years of stellar evolution to set up and less than a second to execute. The wedding ring on a finger, the gold connector inside a computer processor, the thin gold leaf on the dome of a state capitol building. Each atom was assembled in a neutron-rich wind, moving at a third of the speed of light. In a kilonova that occurred somewhere in the Milky Way or its vicinity between 1 billion and 10 billion years ago, drifted through interstellar space in a cloud of gas and dust, incorporated into the forming solar system, concentrated by geological processes into an accessible deposit, and extracted by human industry over the past few thousand years. That is the full trajectory of a gold atom. From synthesis to use, measured in billions of years and light years of travel, scarcity, in this case, is the direct physical consequence of a chain of cosmic events that is genuinely rare. Every gram of gold is the record of a specific moment in the history of the Milky Way, a moment that cannot be reproduced, replicated, or shortened by any process available to any civilization. However advanced, GW 170817 resolved a question that had been open for decades. Do neutron star mergers produce R process elements? The answer is definitively yes, but the resolution of one question, in science, tends to expose with new clarity the depth of the questions that remain, and the field of kilonova astrophysics is currently in a state of productive uncertainty. One confirmed event, a handful of promising candidates, a rapidly developing theoretical framework, and a growing set of observations that are beginning to stress and refine that framework in interesting ways. The first open question is the relative contribution of different astrophysical sites to the heavy element inventory. Neutron star mergers are confirmed R process sites, but the question of whether they are the only significant ones, or merely the dominant ones in the current universe, remains genuinely active. Certain classes of supernovae, specifically those involving rapidly rotating, strongly magnetized, collapsing cores called collapsar events, or magnetorotational supernovae, may produce R process elements under conditions distinct from but related to those in kilonova ejecta. More significantly, some models of the chemical evolution of the early galaxy suggest that at very low metallicity, when the galaxy was young and contained very little iron, in the first billion years after the Big Bang, neutron star mergers alone cannot fully account for the observed R process abundances in the oldest, most metal-poor stars. Those ancient stars seem to have been enriched with heavy elements before neutron star merger rates could have been high enough to explain the enrichment, suggesting that a faster, more frequent R process source was operating in the early universe, one that may have faded in importance as the galaxy matured. The debate matters because it determines how the heavy element abundance of the universe evolved through cosmic time. Whether gold and platinum were always as scarce relative to lighter elements as they are today, or whether the early universe had a different balance of synthesis sites that shifted as stars of different masses evolved and died on different timescales. The answer is encoded in the spectra of ancient stars, in the composition of metal-poor stars in the galactic halo that formed in the first billion years of the Milky Way's history. And reading it out requires measuring elemental abundances in stars with enough precision to distinguish the contributions of different R process sites. Current surveys of ancient stars are beginning to approach the necessary precision, but the picture remains incomplete. The second open question concerns the deep interior of the collision itself. What happens in the milliseconds immediately after the two neutron stars touch, and what that tells us about the fundamental physics of nuclear matter. The outcome: immediate collapse to a black hole, brief, hypermassive neutron star, or longer-lived merger remnant, depends on the equation of state of neutron star matter, which describes how pressure responds to density in regimes that no laboratory experiment can access. The equation of state is one of the outstanding unsolved problems of nuclear physics. Connecting the well-tested physics of atomic nuclei at normal densities to the completely unknown physics of matter compressed to several times nuclear saturation density in neutron star interiors, gravitational wave signals from neutron star mergers encode information about the equation of state directly. The frequency and duration of the post-merger gravitational wave signal, if it could be detected, would constrain the radius of the neutron stars and the pressure-density relationship at their centers in ways that no other observation can. The current generation of gravitational wave detectors, Advanced LIGO and Advanced Virgo, lacks the sensitivity to detect the high-frequency post-merger gravitational wave signal from events at the distances where most kilonova detections occur. The next generation of detectors, the Einstein telescope planned for Europe and Cosmic Explorer planned for the United States, will be sensitive enough to potentially detect this signal and open a window onto the physics of matter under conditions more extreme than anything in the accessible universe. The third open question is the full elemental inventory of kilonova ejecta. What exactly comes out? In what proportions? And how much that varies between different merger events. GW 170817 showed strontium. The kilonova associated with GRB 230307A showed tellurium. Both are heavy elements, but they sit at different positions on the periodic table and probe different aspects of the R process. The systematic identification of individual elements across multiple kilonova events, building up a statistical picture of the R process yield as a function of merger mass ratio, and spin, is the observational program that will eventually allow a complete accounting of the cosmic heavy element budget. That program is limited primarily by the availability of atomic data. Precise measurements of the optical and infrared spectra of heavy elements, particularly the lanthanides and actinides, that is needed to identify elemental signatures in kilonova spectra. The James Webb Space Telescope has significantly expanded capability in the infrared, but even with Webb, identifying individual heavy elements in distant kilonovae remains at the edge of what is currently possible. Then, in August of 2025, something happened that suggested the universe's library of kilonova-related phenomena was considerably richer than the single event of 2017 had implied. On the 18th of August, the LIGO-Virgo CAGRA gravitational wave network, the international collaboration of detectors now spanning 3 continents, registered a signal designated S250818K from a source 1.3 billion light-years away. 1.3 billion light-years means the signal had been traveling since before complex animal life existed on Earth, carrying information about an event that occurred when the most complex organisms on this planet were single-celled. The signal was anomalous in a way that immediately captured attention. At least one of the merging objects appeared to have a mass below 1 solar mass, lower than any known neutron star and lower than the theoretical minimum mass for a neutron star formed from stellar core collapse. The source did not fit cleanly into any existing category. The optical counterpart, designated AT2025ULZ, initially displayed the characteristic signatures of a kilonova: the deep red glow, the fading timescale, the spectral features consistent with heavy element synthesis in neutron-rich ejecta. For 3 days, every indicator pointed toward a kilonova, and the community analyzed it accordingly. Then, on the 4th day, the object began brightening rather than fading, and its color shifted from red toward blue, the spectral signature of a supernova rather than a kilonova. The leading interpretation is a scenario that had been theorized but never directly observed, a superkilonova, in which a massive star's final core collapse creates a neutron star, but with a companion neutron star already present in a very tight orbit. And the two merge, essentially simultaneously with the supernova. A compound event producing both a supernova explosion and a kilonova in the same system within the same few seconds. The low mass of one of the components might be explained if the first neutron star had been stripped of mass by previous interaction with its companion, or if the binary had an unusual formation history. If the interpretation is confirmed by further observation and modeling, it would represent a new channel for heavy element production, one that could operate on shorter timescales and at higher rates than isolated neutron star binaries, potentially explaining some of the anomalous heavy element abundances in ancient stars that standard kilonova models struggle to account for. The universe, it seems, has arranged more than one path to the forge, and most of those paths are still being mapped. There is a version of the cosmic origin story that circulates in popular science writing in a soft, poetic register. You are made of stardust. The atoms in your body were once inside a star. We are all children of the cosmos. And while that version is true in its essentials, it is incomplete in a way that obscures what is genuinely remarkable about the specific atoms that make up the heaviest elements in your body and your world. The version that leaves out the collision is a version that omits the most dramatic chapter. Stardust is mostly oxygen, carbon, nitrogen, and hydrogen, the products of stellar fusion, which is a relatively common and well-understood process that has been running in hundreds of billions of stars across most of the age of the universe. The elements that fuse in stellar cores are cosmically abundant, precisely because stellar fusion is so common and so continuous. Carbon and oxygen are everywhere in the universe, in gas clouds, in the atmospheres of dead stars, in the composition of planets across the galaxy, because billions of stars have been steadily producing them for 10 billion years and scattering them through stellar winds and supernova explosions. When someone says you are made of stardust, they are pointing at a process that has been running so consistently and so universally that its products are ubiquitous. That is true, and it is genuinely wonderful. But the heavy elements are different in kind, and the difference matters. They formed in a single second of concentrated violence, in a temperature and density environment that exists nowhere in the universe except at the collision point of two neutron stars, for a duration measured in milliseconds, in a volume comparable to a small city. Then they dispersed at a third of the speed of light into a volume of space measured in light years, diluting to concentrations so low that the probability of any particular atom eventually finding its way into a particular rocky planet, into a particular geological formation, into a particular organism, is the kind of probability that makes the word astronomical mean something concrete. And yet here they are, the iodine in your thyroid gland, element 53, assembled in a kilonova ejecta wind somewhere in the Milky Way's history, regulates your metabolism, your body temperature, your heart rate, your neurological development in the womb. Every human being who has ever lived has had kilonova-synthesized iodine in their thyroid. The same journey through interstellar space, through the pre-solar cloud, through planetary formation and geological time, through the ocean and the biosphere and the food chain, applies to barium and cesium and tellurium and the heavier isotopes of xenon that show up as anomalous ratios in primitive meteorites. Those anomalous xenon ratios, measurements that planetary scientists make in meteorite samples recovered from Antarctica and the Sahara, are the preserved isotopic fingerprints of specific R-process events that occurred before the solar system formed. The pre-solar grains that carry those signatures are literally pieces of kilonova debris material that condensed in the ejector wind of a neutron star merger, floated through interstellar space for millions of years, and was incorporated into an asteroid body without ever being mixed into the solar system's general composition. They survived 4.5 billion years inside the bodies of asteroids, and we have recovered them and measured their isotope ratios in laboratories on Earth. And from those measurements, we can read the signature of the specific R-process conditions under which they formed. You are connected to those measurements. The atoms in your body are samples from the same population of material. The uranium at the bottom of the periodic table, element 92, the heaviest naturally occurring element, was assembled in the same neutron-rich cascade as the gold on your finger, in the same category of event, by the same process. It arrived in the pre-solar cloud, incorporated into the forming Earth, stayed distributed through the mantle and crust because of its chemical affinity for silicate minerals, and has been decaying steadily ever since, releasing energy at each step of its decay chain, which runs through thorium and radium and radon and polonium and bismuth before arriving at stable lead. That decay chain has been running for 4.5 billion years, releasing heat that flows upward through the mantle, drives the convection that moves the plates, creates the mountain ranges and ocean basins, generates the volcanic outgassing that maintained the atmosphere, and sustained the geochemical cycles that made the long-term habitability of the surface possible. There is a specific and remarkable connection here that is easy to overlook. The conditions that allowed life to evolve on Earth, liquid water at the surface, a carbon cycle that stabilized temperature across billions of years, a magnetic field that deflected the solar wind, a tectonically active surface that recycled nutrients back into the biosphere. All of these required the Earth to maintain geological activity across the entire span of evolutionary time. A geologically dead planet, like Mars, loses its magnetic field, loses its atmosphere to solar wind erosion, and becomes a cold desert incapable of sustaining complex life over geological timescales. Earth maintained its geological activity because it contained enough radioactive heat to keep the mantle convecting. That radioactive inventory, primarily uranium and thorium, was delivered to the Earth from the pre-solar cloud, which contained it because kilonova events had scattered it through the galaxy billions of years before the Sun formed. The kilonova that produced the uranium keeping the Earth alive is not a historical curiosity or a poetic metaphor. It is a causal link in the chain of physical events that produced every living thing that has ever existed on this planet. The heat it generated during a fraction of a second of nuclear synthesis, converted into binding energy in neutron-rich nuclei, then released gradually over billions of years of radioactive decay, is the energy budget that has kept this planet habitable long enough for evolution to produce complex life. The volcanoes you have seen photographs of, the earthquakes that reshape coastlines, the mountain ranges that channel the rivers that define the geography of civilizations. These are the visible surface expressions of a thermal engine running on kilonova debris. The gold on your finger is older than the Sun by at least 1 billion years. The uranium in the Earth's mantle is actively sustaining the geological processes that keep the atmosphere functional. The tellurium detected by James Webb in the spectrum of a distant kilonova is chemically identical to the tellurium in the Earth's crust, produced by the same process, scattered by the same mechanism, incorporated into different planetary systems by the same gravitational collapse that forms all star systems. The strontium identified in the spectrum of GW 170817 the first direct observation of our process synthesis in real time, is the same element that colors fireworks red, the same element that dentists used in earlier generations of toothpaste formulations, the same element present in trace quantities in the mineral apatite in your bones. The question that opened this story: how does something that happened 100 million light years away end up on your hand? Has an answer that turns out to be both simpler and stranger than the question implied. It ends up on your hand because the universe has been running kilonova events for most of its history, because the galaxy has been slowly enriching its interstellar medium with the products of those events across billions of years, because a cloud of that enriched material collapsed to form the solar system 4.6 billion years ago, because the Earth formed from that cloud and geological processes concentrated the gold into accessible deposits, because human civilizations discovered those deposits and developed the metallurgy to refine the gold and the cultural practices to value it, and because at some point in the long chain connecting a neutron star collision to a jeweler's workshop, a specific piece of metal was shaped into a ring. That is the full answer. It is not mystical. It is not metaphorical. Every step in that chain is a physical process with a physical explanation, and every step has been, to varying degrees, confirmed by observation. The collision happened. The gold was made in less than a second. The debris spread across light years of interstellar space. It drifted for billions of years until gravity gathered it into a new solar system. It fell into a forming planet and descended through geological time to a point where human hands could reach it, and a species that had spent most of its history unaware of any of this developed. Within a single century, the physics to detect the gravitational waves of another merger happening in real time, the telescopes to see the ruby glow of freshly synthesized gold in spectra from 1 billion light years away, the analytical tools to trace the decay heat of uranium through the interior of their own planet, and the imagination to look at the ring on a finger and understand, with genuine and precise comprehension, that the atoms it contains are older than the star that gives them light. That is where gold comes from. That is why it is rare. That is why the Earth is still geologically alive. And that is what it means to say that the atoms in your body have a history, because the history is real. It is violent. It is beautiful. And it is longer than you will ever quite be able to hold in your mind all at once, somewhere in the Milky Way. Right now, 2 neutron stars are orbiting each other, spiraling imperceptibly closer with every revolution, losing energy to gravitational waves at a rate too slow to measure across a human lifetime, separated today by a distance that will be in 100 million years. Nothing at all. The spiral is already underway. The outcome is already fixed. The gold that collision will produce already has its destination somewhere in the future of this galaxy, in the composition of some star system that will form from whatever molecular cloud absorbs the ejector, perhaps orbiting a star that will shine long after the sun has gone cold. The forge is still running. It was running before the Earth existed. It will be running long after the last human civilization has dissolved back into the interstellar medium from which it came. That is the universe. That is where your gold comes from. And now, at last,